First of all, hello.
Hello.
We're not having class Tuesday by schedule plans, so you don't have to be there. Is that good or bad, Lou?
No, my airplane was on Wednesday. I thought you were going to have that class.
What was it? Your airplane is on Wednesday?
Yeah.
Oh, I'm sorry. No, that's one thing I did try to put in the syllabus where we weren't going to have class before Thanksgiving for this reason. Maybe you can change. I don't know.
It's okay. I don't have to proposal.
Okay, even better. So yeah, no class Tuesday, mainly because Thanksgiving week, tough. So don't come Tuesday.
Okay.
And Thursday?
Thursday of next week is
We don't have
Hold
that.
on.
is a state holiday.
Yeah.
So,
Okay.
which is sort of a unique
What are we gonna have?
unique holiday in the United States, and so I know that, why would we have Thanksgiving? I don't know. It's just a tradition, right?
Oh,
So
we need to eat turkey.
turkey. I don't know. Is everybody into turkey?
Yes, turkey legs.
Yes, the legs are good.
Mm-hmm.
So yeah, we're not going to have class Tuesday, even though I know that we've missed a couple classes this year. I'm just going. I have that in the syllabus. I don't want to. If you have made plans around it, I don't want you to change your plans. So that's the first thing. Second, do you have any questions for me about homework or structure or anything else? So give me a chance to have a bite.
Lou is going to ask you.
Who is?
No, it's a homework 6 question 13 didn't work out. So
Uh-oh. Let's find it. Question 13. Scaled modification index. So it should be the second column over, mi.scaled. Are you using that one?
is it this?
Mm-hmm. Yeah. And the number is going to be over here, this column.
Okay. And then-
mi.scaled.
Yes,
Okay.
and then the highest one, right?
The highest one.
And
Yeah.
then it's just the one.
I'll have to look in. Send me an
Yes.
email. Yeah.
Okay.
This is homework 6?
Mm-hmm.
Amy, what are you doing so early?
No, I skipped homework 5
Mhm.
to the homework 6
Mhm.
because more encouraging,
Mm.
and then it's just not working.
Homework 5 is not online.
What's that?
Homework 5 is our own data.
Your own data.
Yeah.
Should be a fairly straightforward analysis, I hope. Send me an email and I'll take a look
Okay,
at it.
great.
Or, hang on. No, I better not do that.
Yeah.
Well, screw it. Hang on. Dum, dum, dum. Everybody's going to see my answer key. Look out.
Oh please, it's boring.
No, no, it is. Let's see here. My biggest fear is whether I put cuss words in here or not.
Mhm.
Did I swear? Oh, you know what? I didn't. Yeah, let me send me an email. I'll see if I can do it. And also
Okay.
send your code, please. Too.
Okay.
You guys want to see what I was working on before this? See if I can do it. Nope, didn't work. Hang on. Yeah. Go away, go away, go away. Don't save. Hide. Sort of like our class, by the way. But this is this is a path model, a structural equation model, but with where the factors are all binary. And so these are things that students may or may not have mastered along a standard. And so they take assessments and different grade levels and so forth. And if you have a student who's taken one that's down here, maybe at the 7th grade level, how does that change the plot of what mastery is? So green means they've mastered the content area, yellow means it's uncertain, and red means they haven't. Kind of fun, but details. Okay, other thoughts or questions? What do you know about measurement and variance then?
What don't you know about
What don't you know? That's even better. Excuse me. What do you remember? Do we have to just throw our hands up and say, forget it?
We have 3 set types of analyses.
Mm-hmm. Start with factor loadings, move to intercepts or thresholds, move to residual variance. But in the philosophy, why do we have to do that? Because when you're talking to your advisor and you're like, I'm going to do my dissertation, I'm going to show that there's group differences on this factor. And here's how I'm going to do it. And your advisor's like, why are you doing all that? Is that really necessary?
Test for generalization.
I think it's to remove a confound. Right? You want to make sure that group differences on the factor are truly group differences on the factor and not reflective of differences in the item themselves. Or if you think about the 3 different types of analysis, we started with factor loadings. We need to have a set of factor loadings that are non-invariant, that are invariant across groups, to say that the factor, the trait means the same thing. That we're not comparing, apples to oranges or some whatever cliche that you want to use to make that work. So part of it is you want to remove the confound of, actually, let me ask you this. What do you think happens if you ignore measurement invariance and test for differences on the factor? Like if you just say, you know what, I'm going to keep all my factor loadings, intercepts, residual variances the same across groups. I'm just going to go and test the mean difference on the factor.
Show you differences in the trait that aren't necessarily true differences in the trait.
That's it. Yeah, it could be if you have a big difference in some of those parameters that you've fixed to be equal across groups that shouldn't be there. The only place it can show up then is in the mean of the factor. And sometimes, it's big, sometimes it's small, but overall you want to make sure you remove the potential for confound. So when you argue this, what you're trying to say, I need to worry about the confound of measuring the same thing and measuring it the same way across groups. That's why we need these steps.
So the intercept invariance or scalar
Mhm.
invariance, that is removing confounds that might be present in the intercept.
Mm-hmm.
You have to respond right now.
Pardon me for eating in front of you. Yes, we were looking about, when we get to, let's imagine we've done metric invariance. We see the factor loadings are all the same. When we get to the intercept, the scalar invariance, and the confound for the scalar invariance, but remember what happened when we equated all the intercepts to be the same across groups, we also freed the factor mean. So what's going to happen effectively is if you have a difference in intercept across groups for the items, it may that's really going to impact the difference in factor means. Right? If you have a difference in factor loadings, you're doing 2 things. You're conceptually changing what the factor means, what the meaning of the factor is, but the factor variance changes from the factor loadings, right? So the factor loadings are tied to factor variance for the most part. Intercepts are tied to factor means. And so if you ignore differences in each of those, you're potentially running afoul of the factor mean on the intercept side and the factor variance on the variances side, on the factor loading side.
And configural is just 2 separate, 2 completely separate fields.
That's exactly right. It's like saying I have 2 groups. I'm going to have, if I just did 2 separate analyses altogether, I don't think there's no guarantee it means the same thing across the groups. So, is this helpful? Kind of remember, always want to focus on why we're doing things. I'll pull up the PowerPoint here. Hope to at least. Welcome back. Everywhere. So we talked about residual invariance. And then we did structural invariance at the end, where we talked about the difference in there. So there's certain things that we talk about in invariance testing. There's measurement invariance, which is at the measurement model side. Remember, measurement model is everything to do with where the items touch the factor, right? Structural model, it has to do with things at the factors themselves, right? So structural invariance is whether or not our groups differ in their distribution of the construct of the factor itself, right? And so it's means, variances, covariances, all the other stuff that goes along with it. So that is the CFA version of this. And in just a moment, we'll get into the example that does the longitudinal data. So we want to establish longitudinal invariance because perhaps we want to talk about differences over time in a factor. But just before we do that, I want to talk about the process. If we were to switch our data from continuous to categorical, how the process might shift. Now, there is an example that deals with categorical. In fact, I can pull it up. That is example 7C, I believe. And this is with using the weighted least squares, the Levon version of categorical. And effectively, it runs the same thing. The only difference is there's two differences. Number one, instead of intercepts, now we have the thresholds. Remember the thresholds per item? Right. So in these data, these are the data that we looked at in our example for item factor analysis. The 7-item assessment of daily living, activities of daily living scale. And they were 4-point Likert scale. 0, it means I can't do it. 1 means big problems. 2 means some problems. And 3 means no problems. So we go along with the assessment and we see the factor loadings work the same. We test them first. Then so that's metric, metric invariance. I always get metric and scalar mixed up. I want them to be opposite. Factor loading invariance comes first. But when we get to what would we call intercept invariance or scalar invariance, it's now invariance on item thresholds instead of intercepts. Right? So there's a lot more of those. Right, before every item had 1 intercept. Now in this analysis, every item has 3 thresholds. But it still works the same. What you'll find, though, is when we get to residual variances, this is where things shift. In a categorical item, the residual variances don't really exist. So that last step of measurement and variance where we looked at the residual variances, the unique variances, to see whether they were different across groups. And I sort of said whether or not, this was in the PowerPoint slide, it talked about whether there's something called strict invariance, right? Strict factorial invariance. In the categorical data world, that doesn't exist. Or if it does exist, it's hard to understand what it's doing. Like, if you pull up the M+ slides, M+ will let you do a little bit more with it than Levon, but they still get pretty funky. It's sort of just a throwaway. So the two big, but then after that, the structural invariance works the same. You test the factor loading, you can test the factor means, you can test the factor variances, so forth. So, long story short, what we said for CFA applies when you have categorical data. The exception being, instead of intercepts, you now have thresholds, so there's usually a lot more parameters there. And you do not have the residual variances. Cool? Maybe? Anyway, you can take a look at this. I did not assign this as part of homework 6 because honestly, these analyses make me so grumpy. I don't know about you. There's just so many models, so much going on. But they're needed, so that's it. But in an item factor analysis, so the things that we would do in Levon, or the default in M+, we'd still call this invariance testing. However, if we were to do things from the item, if we were trained in the item response theory world, which is a lot of people in my program deal with that, we wouldn't necessarily call this invariance testing. We'd call this differential item functioning, and they're synonymous. Basically, to do differential item functioning, because it's attached to item response theory, the big difference between the two is instead of looking at thresholds for invariance, because IRT, they typically parameterize their model with discrimination and difficulty. The threshold now becomes item difficulty. So you're looking at invariance of item difficulty rather than invariance of threshold, but effectively it means the same thing. Right? It's usually interpreted the same way. The other difference is a lot of times in IRT we use maximum likelihood, and I wish Levon gave us that option because it works a little bit differently. If you want to do that, there is an example that Lisa built, example 7D, that's online, that shows you how to do the invariance testing with maximum likelihood in IRT. But it's only on M+, and we're not gonna go into that in this class because it's just more and more syntax, and least squares is good enough for right now. If you really want to get into it, you can talk to me, or you can go through the example. So, are we cool? Cool. I feel like I'm. So is this fairly understandable apart from being overwhelming? It's building upon. It's like just building upon what you should have. I hope I've been helping you learn. Not should have learned, but if I'm doing my job right, I'm hoping that you've had a certain level of it before. It's now just really laying it on. Like you talk about before, we said, oh, we could model fit test this, we could compare a simpler model or whatever, and it was a nice, cute thing. But now we're doing that like every step, right? There's Anova functions, and there's just all this other stuff. So back to the slides. Differential item functioning is sort of the flip. If you want to go and compare the two, measurement invariance, the word invariance means the parameters are invariant across groups or across whatever you're testing them for. Whereas differential item functioning means really the parameters are non-invariant across groups, right? Just the language itself works that way. And so, hey, look at that. My table for 2 is booked. Great, I got a text from Open Table telling me tomorrow night's dinner's already taken care of. Anyway, I don't know why that matters. Yeah. Thanks. It really needed to tell me that. I should have put my phone on silent. Anyway, sorry. Thought you'd appreciate the randomness. Yeah. Anyway.
Wow.
Yeah. So IRT, they start to get into a couple different words I really want to tell you about. One is called uniform diff, which is effectively changes in the item difficulties. When that happens, what you'll see is the item characteristic curves look the same. It's just for one group, the difficulty is shifted over. And so that's really just, if the item characteristic curves look the same, the only way that they're different is, they have the same slope. The only thing that can be different is the item difficulty. The opposite of uniform diff is non-uniform diff, where they have different shapes altogether, right? But so those are buzzwords that you hear. I wouldn't get too hung up on it. If you know one of the methods of invariance, you can map it to the other if you ever have to. I always just kind of go. It's like your native language, whatever you know. If you have to, if you have to go abroad to grad school, you know, and into a place in the middle of a weird country and speak English, you can. But you know, if you go back to your native land, including Utah and California, it's you can speak your native tongue, but you know everything's represented. That's what I'm trying to say. There's a translation for everything, and yes, it may take a little bit of time to hear. If you walk into a room and you're familiar with measurement and variance, and everybody's talking about differential item functioning, yeah, there's a little bit of a translation that happens to happen, but the concepts still carry over. Right. I would say it's probably less of a translation than pretty much any language to English, from what I understand, but who knows? That's one of my hobbies. I'm trying to learn as many languages as I can very poorly. So have you seen the app called Duolingo?
Mm-hmm.
Yeah, so I've made it through Spanish, French, and I'm getting on Italian. And then the next one, it's like now they have like some of the Asian languages, and I'm like, oh, which one? It's like Japanese is there. Like, oh, maybe I should do that next. So I've only fixed the Romance languages, the ones that I should, as a native English speaker, have a better shot of be able to have an app help me with, right?
Do you think your conversation?
No.
Well, that's good Spanish.
Ironically, I mean, I can use Spanish poorly in town. When I was a kid growing up in California, you'd think I'd learn Spanish, but no, my elementary school had French.
Mm-hmm.
Sacramento, California, elementary school had French. Now I went to another elementary school. There was a little bit of Spanish, but then in high school, what did I take? Well, I took French before, so French. So because I took French at an early age, I feel like it's much easier for me. I feel like I have a better chance of at least understanding what people are saying and maybe creating speech. But yeah, you'd think with Spanish I should know Spanish, but no. Anyway, so yeah, I don't know why I got off topic there. Different language. There we go. Okay, so let's talk about what happens though in longitudinal data though. So let's look at example 7b. So this is with the confirmatory factor analysis. So again, we're going to deal with intercepts instead of thresholds. So we're going to have residual variance. And now we're going to take an example where we have a test of social functioning at 3 time points. So we have 151 people, took 6 items that we're going to pretend that are continuous across 3 occasions. What's that? So we're going to do CFA. And actually these 6 items are really 6 subscales. So basically we're doing a bunch of parceling. Or these are factor scores from this. The subscales are social competence, social interest, personal neatness. Those are positive things, and negatively related things of psychoticism, motor retardation, and irritability. Ironically, I'd probably be high on irritability. So what we are going to do is form a general factor out of these. But we're going to do the longitudinal analysis, unlike what we've done in the previous example, where we had each person, we had a group variable that said, group 1 and group 2. Now we don't have that. We have a person's data. They have 18 pieces of data. Right? There's no grouping for them. It's just essentially there's 6 items at time 1, there's 6 items at time 2, and there's 6 items at time 3. So we have to set this up a little bit differently. But why this is important is if we're going to talk about changes in this overall trait across time, we have to establish that the trait itself, the nature of the trait, isn't changing across time as we go. Right? It's like saying, in education, do you think there's these things called vertical scales? Have you seen these before? Ever heard of these vertical scales? It's the idea that we're going to take a content area like math, and we're going to put people from 3rd grade to 12th grade on the same scale. You would like to say, oh, a 3rd grader, yeah, they're probably going to be on the low end of the scale. But the 12th grader should be in the high end, and then we can sort of measure growth. There's sort of an assumption, there's not just sort of, there's an explicit assumption that has to say that scale, math means the same thing at 3rd grade as it means at 12th grade to be able to do that. I'm not convinced of that, personally, but that doesn't stop people from doing it. Right? And so because of that, you can think of this as sort of a method we could use to test that. Does math mean the same thing at each grade level? Or in this case, does social functioning mean the same thing across 3 occasions? Right, so we're going to have this. Now you'll note this is not exactly precise because with a lot of longitudinal data, you don't just have time 1, time 2, and time 3, and everybody is exactly the same distance apart. Right? Time 1 is exactly the same distance from time 2, and time 2 from time 3. Right? Each person has a different set of time, so this is not as precise as we could be, but we're just going to lump it into 3 categories of time for right now to get the general picture. That sound good? Any questions on the setup? All right. So we're going to assume this. Step 0. We're going to assume that the trait means the same thing at each time. There's 1 factor at each time. Right? So our 3 groups, even though they're the same people, same 151 people at time 1, time 2, time 3, we're going to pretend there are 3 groups, right? Same person across time, but 3 groups.
And just make sure that what you would put out line, that all of those lines would be parallel. Correct? Okay.
Group 1 equals group at time 1.
Right. So basically, we're going to have 3 factors: the factor at time 1, the factor at time 2, the factor at time 3. And we're trying to see if they mean the same thing across time points. But what we really need to do is to test whether our item parameters, test measurement invariance across the time points.
So it's if we graph this line, it would be like a slope, like a line for each group that is all parallel to each other.
Right. Well, actually, we're going to do a little bit different. It's not just the line. We could do the line, the linear trend, but we're going to allow it to have different parameter values at each time point. So instead of the line, we're just going to say time point 1, like when we get to, let's take a look. The Configural Model. What's the Configural Model doing?
30 separate CFAs.
Yes, exactly. And how we code that is to allow effectively a different factor loading at each time point. It's one big, the way the syntax is going to work, we're not going to be able to use the group syntax in Lavon because we don't have, like our data, one person is on a line in our data frame, and we don't have a group for it. So we're going to take we're going to trick Levon into doing a multi-group analysis, but we're going to trick it by saying there's 3 factors, right? And to the extent that the item parameters load onto the factors the same, Levon won't actually have 3 factors. It'll only have 1. If everything was equal across all the groups, it'd be like 1 factor just 3 times, right? So our Configural model, in effect, it estimates all the factor loadings, all the item intercepts, all the residual variances separately for each time point. Further, in the longitudinal invariance, it's customary to allow items across the time points to have a residual covariance across time. So what am I saying here? Let's take a look at item 1. We're going to allow it to so this is V1 T1, means variable 1 at time 1. We're going to estimate its covariance with variable 1 at time 2 and its covariance with variable 1 at time 3. And then we're also going to take the covariance between item 1 at time 2 and item 1 at time 3. And we're doing this because those are like miniature methods factors, right? Because we've seen the same variable at 3 times, maybe we need to control for the same exposure to this item. It sort of allows us to get away with this analysis a little bit more.
So this like the residual head, the interpretation of the residual head is associated with the time.
Mm-hmm.
So we want to partial out the time effect.
Mm-hmm.
It's the same as time series.
You would think that, yeah. Mm-hmm.
Okay.
This is, it's allowing effectively the idea that because the item is the same across the 3 time points, that the factor may not describe all the differences of the variation. It could also be familiarity with the item. So if a person is more familiar with the item, it might become more, their responses may become more patterned than what the factor would say it has to be.
It's kind of, I'm not sure, but I have a generic understanding,
Mm-hmm.
reading about multi-level modeling.
Mm-hmm. Mm-hmm.
It's kind of the same thing, but the multi-level modeling will allow different, it's okay to allow different slope. Okay.
Right,
But
yeah.
the bar is to explain this slope in each.
Yeah, no, it is like actually the CFA model is a multi-level model, believe it or not. But
Yeah,
but we don't need to go in there. But yeah, we're letting the factor. We're trying to think what influences the variation on a person's score at a given time, and what's going the prime influence is that the trait level, like the factor level at that time. But then there's all these competing influences, right? We talked about before negatively worded items or methods effects.
Yeah.
One of the big method effects here is just repeated familiarity. You know, if you keep seeing the same question over time, are you going to settle into a response pattern that's not necessarily driven by the factor level, but it's also familiarity with the item itself? So we're trying to build that into the analysis as well. So the Configural Model syntax, we have 3 factors. Each has its own loading. Each has a loading for each item. And so because we're estimating the loading for each, you can imagine what we're doing with the factor mean and variance each time. We're saying the factor means are fixed at 0, the factor variances are fixed at 1 for each time. So we we standardized factor identified this. All the intercepts are estimated separately for each time point. All the residual variances are estimated at each time point separately. All the residual covariances are. And then finally, we're going to estimate the factor covariances across time as well. And this is what we call our Configural model. This is the main primary model. And what you're going to see with this example, this is real data. This example is not going to look nearly as pretty as the Brown book example where we had everything be invariant. Not at all in this case.
Which is good.
Yes, I think it's much more appropriate. So our CFI and TLI are 0.90, 0.91. They're not great, but we'll go with it. RMSEA is 0.99. You see people report this type of level of information. But this is like saying that because our factor loadings are measured separately across times, this is like saying we have 3 separate factors altogether. Right? That's it. There's our Configural model. What comes after Configural? What's the metric? You saw it down there. Not that you wouldn't, but what do? We anchor all the items together. Now you'll note, because I have these factor, time 1, time 2, and time 3 is a factor, I'm not using the group syntax. I'm not saying group equals in Lavon up here. And when I submit to Lavon, there's no, it doesn't know this is a multi-group model. But I'm tricking my model to be multi-group by the way I'm structuring it, right? So we then constrain the, yes, Shada.
So the configural model results basically told you that you have 3 separate factors.
Mm-hmm.
What if they don't show 3 separate factors? So what if your TLI, your CFI is 4?
Mm-hmm.
Ish.
Mm-hmm. You gotta try a different configural model. You have to get the model to fit first to be able to do this. Because the configural model will fit the data the best overall. And it's only going to get worse. So if this is your baseline for as good as it gets, there's not really a, you're disconfirming this structure in each of the time points. So you've got to find a different configural. You basically have to play with the factor structure a little bit more to figure out what will fit. That's a big step that we sort of just sweep under the rug. So metric or factor loading invariance, we set the, see I double click it, you see everything's highlighted. Constrain the item factor loadings across times to be equal. Everything else with the exception of the factor variance is the same. But the factor variance, at the first time point we set it to 1 as an anchor. And then at time 2 and time 3, we estimate it. Right, so. Yeah?
It's interesting how you anchor the first one.
You can pick whatever one you want to anchor.
No, I'm not talking about it, but I'm talking about like how the unseen recognition that okay, this is the anchor point, and you need to report around that point.
Mm-hmm. Right. Yeah. It's not real. It's all subjective, right? And that's why I was trying to tell you before. The variance is proportionally scaled, whereas the means are fixed, right? And so, for that reason, you say instead of saying the variance for group 2 is 0.2, really you could say it was 20% the size, right? Because then it doesn't matter. It's regardless of what identification you use, it should still be the same number.
Yeah.
So again, one of the things I noted was you want to make sure that the things you've constrained to be equal are equal. So you take a look at all the factor loadings, they are all the same across time points. And you want to look at the item variant or the factor variances and see that they are different across time points. Right? Time 1 has it at 1, time 2 and time 3 are estimated. So what do you think? Does it fit better or worse? Let's take a look. We do the Anova test, we see a p-value of 0.0385, which is not terrible, but we're going to continue on. Let's just go see.
So this is related to our discussion last time.
Mm-hmm.
Because
we want a low p-value there, yeah. Mm-hmm.
So if we stick like with the from the beginning, if we identified like our p-value is 0.001.
Mm-hmm.
If we find this, okay, we will stop.
Mm-hmm. Well, just to show you how it works, we're going to grab the modification indices, and with all this other code right here, just switches it to look for only the factor loadings. And the thing about this the syntax is the modification indices that you first see have the loading, because we've identified 3 separate factors, time 1, time 2, time 3, which we know conceptually are the same factor. You're going to find that every item's loading with every other factor shows up in the syntax too, like time 1 with item 1, time 2. We're not going to add that loading because that conceptually that's a different time point, right? We can only add the loadings. Pardon me, that's item 1. Here, let me see. I'm restricting it to, yeah, there we go. So we don't want to add that. I'm blanking on what I'm saying. We only want to add take a look at the invariance for, or the modification index for items at the same time as the factor that's stated. All right, this will help us understand which item we need to free. So here, our wait, look at this. I look at the mi.scaled. What this is telling me is that the factor loading for item 6 time 3 tends to have the highest, actually it's roughly the highest, almost the same level as item 1 time 1. So I just picked item 1 at time 1 just to be consistent. And so when I did that, I freed the loading here for time 1. Item 1 time 1. I did not free, everything else is still free. I do the same analysis. I take a look. Now the loading of item 1 at time 1 is 3.22233, whereas the other two loadings are 2.644. Now I look at the Anova result, and lo and behold, it's not, the p-value is very big, and we're all very happy, and yada, yada, yada. I could also look at the modification indices, and you can see there are some that are big and high. Not that big. 3.13 is not big enough to make me all angry. So, how we doing?
0.
Where? What?
Wait, what?
So the p-value.
Yeah, metric estimates to configure.
That's right. Yeah, so I'm comparing the second metric estimate model with the overall configural model, and the p-value of 0.43 says they fit the same.
So, just I'm asking my friend, I not mistaken, the chi-square critical value with 1 degree of freedom is
3.84 for an alpha of 0.05.
So we don't worry about that.
Yeah, the chi-square, so these modification indices right here, if you're type 1, for each test, if you're at type 1 error rate, not the whole family, but for each one test, if you're looking at that term with 1 degree of freedom, because each of these is 1 degree of freedom, the critical value at alpha 0.05 is 3.84. So that's that. But now if you're worried about multiple comparisons and type 1 error inflation and so forth, 3.84 needs to go up higher. The higher threshold, because that's effectively a smaller p-value per test to help. So what we're going to say is there's partial metric invariance. So we only had to free 1 factor loading across time. That's good, right? What do you think? Do the factors mean the same thing across time?
Just
Maybe not.
item.
Yeah. I think that we have a good argument that they do. We're going to see. Wait till you get to the homework. There's all sorts of problems with that, right? Shit.
I'm just thinking that, I don't know if this is like a visual way of thinking about it, but like some sort of like flow chart of like how to do this. Like if this tells you this, then like you need to do modification indices. And if that tells you this, then do this.
I didn't bring I have the iPad, I just didn't get it out, but yes. So configural invariance first, right? And then you go and you do metric invariance. And the question would be equals configural invariance, right? So this is your kind of decision point. I guess this is the triangle, right? Right here. Equal CI. I guess so it's MI equals CI, right? If the answer is
Yes.
no, let's say no. No. Right?
Did I get
Go back. This is
And no meaning your p-value is
this is p is less than like say
Significant.
0.05 or whatever, right?
Yeah.
Or smaller. Right? So now you go back and look at modification indices. Right? But if the answer is yes, right, so this is p greater than 0.05 or something along those lines, then you move on to scalar invariance, right? The same thing happens. The scalar invariance equal configural invariance, right? So the same, no, right? Modification, right? So we're sort of cycling back through this to make this work.
and then within that, so then metric is intercept
Factor loadings.
factor loadings.
I was to say loadings.
That's right.
And this would be intercepts.
And then configural is like
All
number of
three.
separate.
Yeah, separate. I'll just call it separate.
Yeah, does this exist? This is really helpful.
Probably someone has it. I should build it. But...
I'm gonna take a picture.
Take a picture. There you go. Here. I feel like I should put it on my iPad here to put it in the lecture slide. So hang on just a second. Bang. Sorry. Here's the problem. I put soda in here, and then if it falls over, then it starts being the soda flying everywhere. I get it all over. I'm wearing a white shirt. It's going to be awesome wearing soda all day. For those of you who are from the Midwest, pop just still doesn't seem right to me. Who's a soda versus a pop person? Soda?
Soda.
So where are you from?
California.
California. What part?
Southern California. Yeah.
Cool. Midwest. Kansas.
Pennsylvania.
It's a,
Western Pennsylvania says pop.
there we go. All right. So I'm glad that we've all agreed on soda. Those of you who aren't from the United States, I don't. Do
We
you
say soda.
you say soda?
Yes.
Oh, I like you even more now. This is awesome.
Some places they call all soda, they just call it Coke.
That's right. Yeah. Well, I lived in Georgia, which was close to like the home of Coke, and so it was like, let's have a Coke. What type of Coke? Oh, Dr. Pepper. Let's see. All right, we're getting there, I promise. All right, here's what I'm talking about. Let's see if I can take a picture. Nope, you don't want to see that. You want class. There it is. Add a page. Put that down. Insert. Camera. Hey, over here. Okay, right here. This thing.
Wow.
Perfect.
There.
Thank you.
And now, hopefully, it's a little bit of what you can see to make this work.
Where's that gonna go? Just in the notes.
On the notes, yeah.
In
So
the
on the
video.
video, I guess we'll
I guess it's in the video, yeah.
Okay.
In your mind, it'll be a mental representation. I can try to. Could you email me a reminder? I can build something in R that has a nice graph to it, I think. I've just been playing that thing I showed you before with the linked nodes or whatever. I'm sorry.
No,
forgive
it's
me.
okay. I'm
I would
sorry.
make it in Word, but that's just me.
Yeah, well, I can. I like code. No, but anyway, it'll just be there in the example.
Yeah, I think that would be really helpful.
Can you send me an email to remind me? So yeah, this is. So here, this is exactly. This is what we need it to be. This is flowchart. But yes, configural model, loadings. Does it fit? Yes, no. Modification indices, no until it fits. Intercepts comes next, same thing. And then if I were to keep going, residual variance. Right? And the same type of decision process. RV equals CI. No? Yes. Right?
And no modification.
Oh, this would be also modification indices here too, yeah.
And then what if it's a yes? You just wrote yes?
Yes. Then what we get to is structural. And we'll worry about that in just a little bit. But the measurement invariance part, this whole flow chart is a necessity. When you get to structural invariance, if they are non-invariant, that's sort of the story you want to talk about. Do these things differ across groups? Or in our case, in this example, does the factor differ across time? Well, you can think of why we'd want this factor to differ across time. Right? If this is some type of intervention, perhaps this is, we talk about a psychological rehabilitation. I'm thinking people with PTSD might show up, or something, maybe former veterans, and they're trying to, get help about types of difficulties they might have. We'd like to see the factor get better across time, or have less of the trauma across time, right? So that's fine. The structural model is the story that we're after. Whether that's invariant or non-invariant, it's just a consequence. That's the final result. That's why we engage in this analysis to begin with. But all this flow chart that we see here is setting up the structural being okay to say it's different. Does that make-
What's RV equals what?
Sorry, this is my resolution of 10. Residual variance equals configural model.
So none of the analyses, at least on the what's on the whiteboard, are going to actually help you answer a specific question, like a research question. They all are just setting up for you to answer a research question through the structure.
That's exactly right. You're removing the confound of saying that there's a difference in either like the first thing, the loadings. This is saying, are traits same? Right? Are the traits the same across groups, across time, or whatever? Right? Are you comparing the same thing? That's what this is saying. And then this next part is saying, so this is the big one, right? Are the traits the same?
For metric.
Yeah, metric. Metric's like a big one, like it's sort of. But then, so this is sort of removing that confound, like you're comparing apples to oranges. The next are saying, is there some item level difference that would show up in the factor mean, right? So, if for instance the gambling items are good, like the homework that you're going to have, one group is students, one group is not. The trait may be the same thing, the students just don't gamble, right? And some items they just never ever would endorse, where some they might, right? And those are item-specific things. Even though the trait may be the same thing, just as a population they're doing it differently, and the items show up differently. And because of that, we want that to be an item-level difference once we control for it, rather than the trait itself, the factor itself.
So this question would be, are there item level differences?
That's right.
That's interesting.
Just looking at you handling iPad, I want iPad too.
Oh, do you? That's
Yeah.
yeah. I was debating getting the big one, the big ones that look obscene. Like I was like, I still like this little one, even though it's hard because I'm terrible at handwriting and whatnot. I can't. The resolution isn't good. I feel for you. At least it's better than nothing. I'm glad you.
Yeah.
Is this effective as a learning?
Yes.
This is good.
Seriously.
Have fun
That,
both.
yeah, I didn't think of that. Okay.
I love being able to draw, but at the same time, I can't do everything on it. I wish I could do R on it, but not yet.
And then your configural model at the top there, that's not
Christmas lights. Sorry. You don't want an iPad now. The configure model at the top, yes.
at the top there. That there is no question necessarily associated with that. That's just
Yeah. It's a
do
first
this
step.
so you can compare things to it.
That's basically saying this is going to be the best fitting model.
Oh.
Right? So you're setting up the logical argument of saying, I'm going to start the model that I know is going to fit the best, that has absolutely no bearing on really what I'm after. But I need to start here because all of my tests assume the model fits when I start locking down parameters. And so because of that, I need to start completely separate. I fit this configural model as a baseline, and I lock in subsequently from there.
This makes a lot more sense.
That's good. Thank you.
So when you say that this is the best fitting model,
Mhm.
you might do modification for that model to.
Yeah, if the best fitting model still doesn't fit well enough, you
So-
can't do any of this. You still need it to fit somewhat well, because every constraint you make is going to make the model fit get worse, right? Even if it's just a little bit worse, it's still going to get progressively worse. Right? Or, I guess we say it fits as well as. It's that it's like whenever you add, remember in regression, if you had a regression coefficient that was virtually 0 when you add a variable and it changes the R squared by like 0.001. That's what I'm talking about here. Every time that we see that we do this test of invariance right here, we compared the metric model with the configural model. We saw they were effectively the same. But if we were to go back and look at the CFI, let's look at the RMSEA, 0.95 for the model we just fit versus 0. I guess it's got a little better. Oh, never mind. 0.898 for CFI, 0.908 for the other one. Yeah, it got a little better. Yeah, I guess I'm not already shooting myself in the foot with my argument, but never mind. Anyway, it's still, you see where I'm going with this, right? So now, the next step in the flowchart, we've just hit the yes of measurement invariance right here. So we're going to go on to intercepts or scalar invariance. So to do that, again, we leave the factor loading from the last time that was non-invariant. We leave it non-invariant. And we also then say that that item at that time point is just going to be non-invariant. So item 1 at time 1 is just going to get its own item intercept as well. Right? We don't necessarily have to do that, and you'll see debates. It's more important than the categorical data, but let's just be fine with that for right now. What we do, though, is lock in the rest of the item intercepts, and while we do that, we also go and estimate the factor mean. So this is the weirdness in the syntax. When I saw this, I'm like, oh no, we're not estimating it. In the multi-group syntax, to estimate a separate parameter, we need the NA and the C. But because we're not in multi-group, when we estimated the factor mean before, it was just factor tilde 1. So it looks like we fixed the factor mean to 1 because we're fixing the factor mean to 0 in the first group, but this is just the quirk of the stupid syntax. And in Levon, I think syntax is actually pretty good, but overall it's being stupid here. This is actually estimating the factor mean in each group, or it should be. So let's take a look. First thing we do is make sure what we think should be the same is the same. So we look at the item intercepts. And sure enough, item 2 at time 1, 9.368. Item 2 at time 2, 9.368. And likewise. And then you take a look at the means for each. The first time point's mean is at 0. The second and third are estimated separately. Okay. So now we ask the question, does this fit as well as the previous model, or does this fit as well as the configural model? And to both of those, the answer is no. Yeah. Right? So really, the configural model should be our target, but I'm just comparing it sequentially with the model right before it. And we see that we do not fit as well, so we need to look at modification indices. Right, we're in that part of the feedback loop.
No. The no part.
That's right. We're in the no, right here. This part where we might always be. It seems like when you're doing it. Now I have them in order here, and we see that it's item 2's intercept at time 1 looks like it's the one that needs to be freed. Right, so we go to item 2 at time 1. We free its intercept just at time 1, and we redo the process.
Oh, okay.
Right?
Okay.
Oh,
and then
item
you
2.
keep the modifications that you made from the previous one.
That's right.
Sorry, Maine.
That's
No,
right.
no,
Yeah,
no.
we're always.
Yeah, I think we're talking. So item 1. Wait. Item 2, but then only time 1.
That's right. Item 2 only time 1, not across all time.
Okay.
I'm trying to keep as many parameters constant as we can.
So how did you free that one?
I just went, so if you look at the syntax here for item intercepts,
Oh, intercepts. Okay.
yep, we go under the time 2, it's single tilde, but then I just give it a different label at time 1 than I have for the label at time 2 and time 3. So here, what it should look like, if you look over here at item 3, oh, come on, Templin. If I refer to myself in the third person, can it be like a negative term? Can I do that? Does that still make me? Sorry, I have this dream of creating a scale called the sense of heightened importance test. Like the shit. Like, you know, if someone thinks they're the shit, you know, like if the person refers to themselves in the third person, well, Templin 1997 said, no, you know, like that. You know what I'm talking about, right? Like it's like a narcissism, but like, you know. But if I can do that in the opposite, if I could like mock myself, because that, never mind. The syntax here for item 3, you see that I have the same label across each time point. Whereas for item 2, because that first time point needs to be freed, we allow it to have a different label than label 2 and label 3. Right? That, and I also want to publish that test and not like use the acronym. Like see if people would just see it. Yeah.
So when you
Thank you.
decide that you need to make a modification based on the modification indices,
Mm-hmm.
are you always going to make those changes on the item intercepts?
It depends on the parameter. Like in this step, yes.
Okay.
So we're in that feedback loop. If it's not fitting for this section of the analysis, then it will only be on the intercepts.
Because we're in the scalar.
That's right. Mm-hmm.
Okay. Now I get that.
That's right. Yeah, so each section is only in that little section of code itself.
That makes sense.
Cool.
So, I'm wondering, because we did the scalar is like statistically different from the previous two models.
Mm-hmm.
we didn't look at the fit indices, and we didn't go to the next step, which is the residual. We just go to the modification indices, and
That's right. The model fit's going to be roughly the same. I mean, it got worse, but it's worse because the parameters need to be freed. But when this model, if we were to make it fit as well as the configural model, conceptually it should fit roughly the same absolutely with the data as well. All right, this is saying a relative sense. This model does not fit as well as a configural model. But if we get this p-value to be big, conceptually it's saying it fits as well as the configural model. So that should still apply to how well the configural model fit the data. Right, the RMSEA, the CFI, the TLI, and so forth. So sort of a linking of if we tie our standard to the configural model and the configural model already fit the data, then if we say our model fits as well as configural, we have effectively said because of transitivity, our model fits the data also. We could look, but the reason why this model fits worse than the configural model, we know in this case, is because we've modified the intercepts to be equal when they shouldn't. Not all of them should be. So let's see if that next change affected anything. We can look at the output again. Here again, I'm pulling this down because you'll see now the label shows up for item 2 at time 1. And now you see the p-value is less. I'm sorry, it's a little bit bigger, but still bad. So we're going to try again. Now it looks like item 5 at time 2 has the biggest modification index. So again, we change its label, item 5 at time 2, right there. We repeat the process because we're in that never-ending feedback or flowchart loop. And we see the p-value is getting better. Hooray, it's getting better. But it's still not great. So we try again. We see item 4 at time 1 is the highest. We go back, free it, re-estimate it, and oh, the p-value got to be on the good side of p at 0.05. So therefore, clearly it fits. We can move on. Excuse me, I'm so sorry. My crumbs.
Don't worry.
So now we've moved on. It fits. We can move on to residual invariance.
I have a question. I'm sorry, but
Hit me.
when you like in the trade process of modifying the model,
Mm-hmm.
I noticed that the intercepts have different values.
Mm-hmm.
Changed. Why is that?
Because the model doesn't fit perfect, every change that you make to the model causes a ripple effect on all the parameters. Now, if the model was perfect, I mean, by perfect fit, I mean this right here. This statistic right here was like the chi-square was 0. Then anytime you change one parameter, you shouldn't affect the others effectively. But why this is happening is when we put these constraints on the model, we actually have 129 constraints we're putting on the model. The rest of the parameters have to stretch in ways to cover all the possible mean vector covariance matrix of the data. And if they don't exactly, if this, model discrepancy happens, each one of these little places, they're off in different ways. If we free a parameter in one spot and we get a little closer to it sort of reverberates itself through the entire system to change the parameters as well to get closer to where the values need to be as well. So you will see that when you make a model modification, that things change in the rest of the parameters. And that's because you don't have perfect fit to begin with. They're sort of being stretched and so forth. So it's part of it.
So it's kind of rotation?
No rotation at all. It's just a quirk of, if you think of it this way, let's imagine I have four pieces of data. 1, 2, 3, 4. Right? And I say the mean for all, oh no, I don't, no, that's not good. Yeah, let's try it. I'm going to go and, let's imagine we use a simple idea that we're going to use the predicted value for each. We're going to predict the mean with the mean, right? So instead of, here's my 4 pieces of data, 1, 2, 3, 4. The mean of that is what? 4 plus 4, 5, And 10 divided by 4, 2.5, right? So each one gets a 2.5 for their mean. Like, oh, clearly this isn't working, but let's go take number 4 and just give it a 4 instead. So now all of a sudden it's a 4, and I look at the remaining 3, and I try to use the predicted mean of the other 3 to give you the value for what that needs to be. So now it's the mean of, so it's a value of 2, right? So now the predicted value is 2, 2, and 2, and it's closer to where their value should be for each of them. It's still not ideal, but this is what effectively is happening, right? When you go and make one part of it fit well enough, the other ones readapt and then sort of give you an average difference that's smaller for the other parts. Is that
which is also associated with their weight.
right? Yeah, they're reweighting itself to get through. Does that help?
So they average based on the first value.
Mm-hmm. That's right. So this is what's happening here. When we free one of these parameters, we saw the model didn't fit already. So we know there's some big discrepancy somewhere. We allow that to be free. All the other terms, where that discrepancy effectively goes away, and so the parameters that we're filling it in don't get stretched in that direction anymore, and they change.
So they're going to vary every single time.
If we did not have good model fit to begin with, yes. So
Simple explanation.
that was a simple explanation? I didn't know that was simple. I was struggling. Thank you. I was struggling over my words there, but I'm glad. It's sort of, yeah. It's like saying, it's like when if you had all the windows broken out of your car, or on one side of your car, and you put like, I know it's a terrible example, but you put like one tarp on all of it, but then somehow you managed to fix one of them, right? That one tarp on all the windows doesn't work as well as that one tarp on one of the windows, right? It's sort of it's a better approximation because it's, one is fixed and the other one isn't. Is that?
The first one is better.
Yeah, the tarp of broken windows does not sound good. Not sound good. Yeah. Yeah, never mind. I'm reliving my childhood. No, I'm just kidding. No, it's not good. Okay, so let's do residual invariance. We found the last modification that made it work. Hey, all right, we move on. Actually, no, this is Scalar. There it is. This is item 4. So the p-value was groovy, and we moved on. That's right. Now we go to residual. Now here's the thing about the residual invariance. What you're going to see is, again, all the parameters or the items that we had left as non-invariant before, they get their own residual invariance too. Right. So item 1 at time 1, item 1 at time 2, or item 2 at time 1, item 4 at time 1, and item 5 at time 2. They're all getting a separate parameter. The other thing that's interesting to me about this is we allow the residual covariances. We just don't care if they're non-invariant or not. And that's part of the issue. Like the residual variances part, I was mentioning this last time, it matters less than the loadings and the intercepts, because we've run out of parts of the factor it's going to affect. It's going to effectively tell us that one scale is more precise in one group than the other, but that's not going to change the meaning of the factor. It's not going to change kind of how the item differences form. It's just going to be changing the reliability, which really ultimately hurts our power to detect a difference. Right? We want these to be non-invariant because we get better power, fewer parameters to estimate. But if they are non-invariant, like you'll see in the homework, we can still continue without losing the meaning. We just effectively say that there's a different reliability in each group. The estimates here, we can go take a look. Once again, you'll see the variances. You see that the ones that we think should be different are different, and so forth. What's the p-value look like? Oh, not too bad, but let's find that biggest one. The biggest one is item 6 at time 1. So we go and free it by taking item 6 at time 1's label and changing it compared to item 6 at time 2 and item 6 at time 3. We try again. Well, this is a frequentist dream, isn't it? All these hypothesis tests and the Bayesian's a nightmare. Oh yeah, p-value. It's a p-value party. The p stands for party. It's raining p-values. 0.09. Good enough. So next, we've made it through the flowchart. Hooray! Let's check the structural model. Right, the part that we really care about. Yes. No, never mind. TJ, sorry. Shada.
Talk a bit more about the factor variance and variance. invariance
Yeah.
model.
Yeah.
Like I'm with you when we get there, and then
Right. So now there's sort of a debate in my head. Like, do we really what we're testing with this model is whether the variances of the factor are constant across groups. Do we care?
Yeah.
I don't care. But let's just check. If they are constant and we estimate them with one parameter, then we save some degrees of freedom and we have a little bit better power to detect for mean differences.
Okay, so then you run that, and what do you look at in the results? You're looking at the factor variance.
What we want to compare this model right here. This model we have taken the I lumped the variances and covariance together, so it's the covariance matrix the same. So we have the variance is set to 1 and the covariance all set to the same value across times. And what we're going to compare this model with is the result from the previous model.
Yeah. Okay.
And so the result, what this is telling us here, you'll see, is that, hey, look, they're roughly the same. Means the variances across time are equal for the factors. Means the factor itself, the trait itself, is not changing in variability across time. It also means, so that's the variance, the covariance, the traits are the same correlation across time. They're not becoming more or less correlated. But again, that's less the story.
Yeah.
So, but one thing we can do, because this model right here is sort of the end point, we don't need to go and do a likelihood ratio test to test mean differences at this point. So I create the difference in Wald tests. These are called Wald tests. I can create a difference parameter that says the difference between factor 1 and factor 2. Well, the factor 1 was at 0. The mean for it was 0. So if I was subtracting factor 2 from factor 1, it'd be 0 minus factor mean 2, right? If I wanted to look at the difference between factor 3 and factor mean 1, it'd be 0 minus factor mean 3. And if I wanted to look at the difference between factor 2 and factor 3, it'd be factor 2's mean versus factor 3's mean. So this is the mean across time points. So to avoid having to do yet another likelihood ratio test, I just put those 3 tests in, because at the end of the output, they give us these defined parameters, and sure enough, each one of them comes with a p-value to tell you whether or not it's significantly different.
Great.
So here, what we're telling is, this is the difference between factor 1 minus factor 2. All right, so it's factor 1 minus factor 2. That means factor 2 is greater than factor 1 by 0.25. And that would tell you that that is actually significant, right? So you're saying at time 2, the factor mean has gone up 0.25. And because we also set the standard deviation or the variance to 1 for these factors, we can talk about that. This is effectively an effect size, right? It's 0.25 standard deviations higher.
That's what I was gonna say.
Or 0.25 standard deviations higher at time 2 than time 1.
Is this reported? I mean,
Yeah.
Yeah.
You can do that. Yeah, because you've standardized the fact. Because you actually the standard had you not had the factor variance be where it needs to be, you would look over here for that effect size, the standardized column. So it also tells us that the difference between factor 1 and factor 3 is 0.47, and that's significant. And the difference between factor 2 and factor 3 is 0.22, and that's significant. Right? So we're saying, and if you look at this, it's based on time, right? So the difference between time 1 and time 2 is 0.25. The difference between time 2 and time 3 is 0.22. It's almost like a linear trend we have for our factors. Right? We could even test that. We could actually build a linear trend if we wanted to. I'm not going to. I don't care to do that right now. But you could think of this as like a longitudinal model. We could have a growth model for the factors. Growth change of factors, change of factor model that we have. What do you think?
So in this case, it's good to have significant.
Oh well, it depends.
Okay.
It depends on what you're trying to say. If you're looking at
Yeah.
like if you have a cognitively impaired student, and this is something about like learning in the capacity of a classroom, that's probably not good, right? It depends on the story you're talking about.
Okay.
I don't know. I'm trying to map onto the field that you're a little bit more familiar with, but I'm not at all.
Would you get these defined parameters for like 2 separate groups theoretically?
Mhm.
So students with disabilities and without disabilities.
You could definitely.
And say it didn't change
Right.
over time for this group, but it did change for this group.
You could do that, definitely. Yeah, if you had that, that would be, if you think of it, you have the 2 groups,
Yeah.
and 3 time points, it's like a 6-group model.
Right.
And you could do that.
Thank you.
That's exactly right.
So now we subtract time 1 from time 2.
Mm-hmm.
The minus now, because I'm confused. I'm a little bit confused about
Mhm.
this value in favor of what factor, like favoring one what because.
Well, here, let me go over here real quick. Here's the actual means for the time points. Right here.
Okay, so time 2 is higher than time 1, and time 3 is higher than time 1 and time 2.
That's right. The question is, are they significantly higher?
Yeah.
And that's where we need that difference to be. So once we form this difference statistic, it gives us a test of the difference itself. Jihan.
In this example, time 2, time 1, time 2, time 3 have the same time interval, like 6 months.
Mhm.
So we also can test the different time points have different
Yeah.
intervals, right?
Yeah, you could build this where that feature, now it's harder to do. In this model, you can actually do it because you can use the time as a continuous variable. But in a lot of programs, because it's set up to be multiple groups, it's harder to do. In the big picture, because now things we can code, all these models, again, I keep talking about Bayesian, but it gives us flexibility in model. To do a longitudinal invariance where time is unbalanced, we could code it ourselves in JAGS or STAN, and it would work much better than if we did it through a multiple group approach in Levon or M+. Now, there are cases in either of those programs where you could probably trick it to do it that way, but we can do it. We can also do it more directly that way with the Bayesian, because we have better control over what parameters are what. Yeah.
The time 1, time 2, these weighting factors are treated as intercept, like weighting factor or slope factor in the latent growth curve model.
Yeah, but not here. No.
So how would you interpret this factor? What's the meaning of this factor?
These factors are just the actual trait itself, and these are factor differences. There's no slope and intercept. It's a saturated model for the means. Right? So if you're in a longitudinal sense, if we didn't want to saturate this, it'd be one fewer parameter because we have a slope and intercept. Right. But because we allow the factor variances to be free or to test them, we're not worrying about dependency based on time. We've actually built that into the analysis itself because the factor covariance matrix is there.
So I'm not sure, but are we going to talk about monotrate method?
What's that?
Monotrate method?
No, we're not. No. But we'll talk a little bit more afterwards. But you can talk to me about it afterwards if you like. We're sort of running out of time. But effectively, you've got we can talk about this.
Because I imagine it to be a little bit complicated in building because we have one trait but multi-method. So we need to do more syntax.
That's right. Yeah.